This is a Rubik's Cube. Okay, that's not entirely correct. But we can do a curious thing here. Pretend we fill in these curves so that there's surfaces of revolution here. There's no empty gaps. And you see where these intersect? Right along these halfway midlines, midplanes. Here's what we're gonna do. We're gonna color this with 7 colors. You might object, you might say the Rubik's Cube 2x2 has 6 colors. Well, that doesn't have to be the case, and let's prove it. So we color the elements 1, 2, 3, 4, and then 1 over here. This looper all the way around. 2 and 3. So that makes 7 colors. 7 unique colors. Now we have to map the generators of the normal Rubik's 2x2 cube to this object. How can we do that? Well, we just go like this. We slice along each of these like that. Slice it in half, and every time we do that, say we slice here, we're going to take these 4, this top half, and turn it, map it onto itself. This permutes the colors. In order for this to work, we would need 2 color slots for every edge here. For example, if this is blue and this is red, then if we do a turn like this, and then a turn like this, then we would need 2 slots for the colors on one single, edge. So there has to be room for that. Now, I don't exactly have a full colored version, but I do have one, closer thing to that, which is here. So if you're still with me, we actually gain quite a lot here. So in a Rubik's Cube, the standard 6 colors are painted on the flat faces of the cube, and the space lacks any continuous internal structure. You can count the states, but you cannot easily do calculus or spectral analysis for that matter on them. In contrast, we can do a lot of spectral analysis on this. We can look at the cone points and do cone analysis local to those points. We can propagate that dense spectral information along here, along these curves, these geodesics perhaps, onto the skeleton. A lot more can be said, but in this case we gain a lot of analytic and spectral leverage.